Well, all right, welcome back to class 7. This is the third video. We just finished talking about the energy equation, and we did an example, ridiculously easy example, and now we're moving on to section 3.2, titled The First Law of Thermodynamics. And so that they've presented here is the equation that basically covers the first law of thermodynamics. And we're going to take a look at this funny looking integral and what it means. So this isn't too much different from the previous drawing that we had. For many systems, we don't accumulate energy within the control volume. So I think that's what we would want to mention first about this. So that's sort of the difference that we had in the previous energy equation. This is not universally true because maybe we do keep in store in energy in some form or another. But for many systems, this is true, especially for cyclic systems. We will, and if they're like in a steady state, that doesn't mean that they're sitting still. That just means that you show up and then leave and then come back and you have the same conditions everywhere. And so one thing to note is the name of this kind of integral is a cyclic integral. It means you go around the entire cycle, and this is what happens, right? If you start here and then you go beep 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 beep, you go all the way through the cycle, you end up at the same place. You would be able to you would find this amount of things happening. So here's the definition of the first law of thermodynamics. You've probably heard this, but let's write it out anyway. Energy cannot be created or destroyed. But it continues. It is converted from one form into another. That said, I guess maybe Newton would have, I'm not Newton, Einstein would have said, or anyone in the nuclear industry will say, well, E equals mc squared, which would tell you that energy and mass are kind of part of the same thing, and you could turn some mass into energy and the opposite true, but not very easily. And as far as we're concerned, we don't care. We want to say that energy cannot be created or destroyed. It's converted from one form into another. And that's a lot of the times, so as an engineer, that's what we're doing, is we're converting energy from one form and turning it into another form that's going to be useful to us. And so heat and work are the main kinds of energy that we deal with. So if we're mentioning the word work, we should have the definition of work, right? So when I teach dynamics, we have a work energy section, in both in particle kinetics and also in rigid body kinetics, where we take a look at the definition of work. So I always use this, a very specific definition of mechanical work is defined as force acting through, underlined, a displacement x. We don't have right here, they don't show, this is out of the book, so they don't show a dot product right here like I would usually in vectors. But a dot product, when you have two vectors, kind of overlays, like if this is a vector and that's a vector, a dot product projects one onto another, meaning that only the part of this that is in line with that counts. Well, that's what happens usually here, is usually a dot product against the force times the displacement. And that's only the force that's in line with this. So that's why there's force through a distance. So like if you had a force that was going this direction, or where the force was in that direction, but the motion was in this direction right there, it's only that component of the force that's in line with this direction does that actually create work. The rest of it just pulls onto the thing. So, and there has to be motion. So if you just push really hard against something, you're not making any work, although your finger has stored perhaps some strain energy right in there, or the desk did, like that kind of thing. But it's not producing work because you don't have motion. So this is not just position. It's, you can think of it as displacement because it's going between 2 points, point 1 and 2. So force times displacement, force times displacement. And it's path dependent, which is really what we're saying here. It's really kind of dependent on the path. This is the path, and it's dependent on the path right there. So if you have like two points that you're moving between here and right here, and the force was coming up that way, and you went a bump out over there, but in here you went straight. This would matter which way that you were going, the path that you took. So when you say that it's path dependent, that means the history of what took place between these 2 points matters. There's other types of energies where it doesn't matter. In potential energy and kinetic energy, those are types of where it doesn't matter how you get from point 1 to point 2. It's still the same. But this is one that is path dependent. Other forms of energy, we could have electrical energy, right? So we could have electrical work, if you will. That's usually going to be the voltage times the current, but that would be power. So you'd be voltage times the current times the time. And then you would get like what the work you would put out of there. You get rotational energy, and that's going to be a little different. What you end up finding is you get torque times angular displacement. And you go work backwards. No pun intended. You work backwards. Ha ha ha. But you could see that you could find x, right? If you're going in making an arc, right? That this if we we're going to go, what is that? What is the length of that arc, right? So if this is an arc, the x would be equal to r times theta, right? Or you could say that dx is equal to r times d theta, right? That little arc length. And if the force is always in line, like if it started out right where they show it and it ended up like right here where they showed it, it would be traveling through an arc. And that force times the radius, where the radius came from, is also what we call torque, right? So like a torque wrench, or if I trying to think of a way to put, like if we're going to twist this, that's a torque that I'm putting onto there, right? And that's usually found with the force times the distance. A lot of times what we'll do is this is in case, because I know you're taking statics and I'm not sure where you are in statics, but like if you put a force on a wrench right here, and this was your length right here, it would create a torque that went around that way. That would be the torque. So force times the length, it creates a twisting about an axis. It has to be about an axis, usually about a long axis. So if you want to twist a bolt, let's say, you'd get a wrench, and what you're doing is, and by the way, that force has to be perpendicular to that R, just like it has to be right there. So torque times angular displacement is also produces work. And then, of course, as we mentioned earlier, there's rate of work, right? So I didn't write out torque, and I meant torque. And this is angular displacement. So this is the amount that it has twisted. That's the angle it has twisted through right there, right? So you can see that little piece he's twisting through, making that go up to. So that's the amount of work that's been put in there. But we can also have the time rate change of work, which we know is power. And we could look at that in a couple different ways. One is you could take out the force times the distance, right? Just like we did up here. And let's see that now we have the distance per time, which is force times velocity. That's a good thing to know. So like if we had the thrust of the engines of a jet and the velocity of a jet, that would be the amount of power that was being produced by that jet, equal to the amount of power that's being, if it was going this a steady speed, the amount of power due to the drag. You can also separate these things out. And so here's going to be the R times the angular velocity, which a lot of times we'll call omega. That's usually radians per second, but we could also just turn it into RPM, right? So we have torque in RPM. So if you can think of this in terms of power for like maybe a truck, that's why we have gears inside the truck to change the. It's going to have the same power from the engine, but if we shift down in gears, we reduce the speed, we increase the torque, right? So that like if you had if you were hauling something behind and you're going up a hill and it's like the engine's fighting hard, you can shift down in gears to go to a slower gear to reduce this, and with given the same amount of power, you'd increase the torque and be able to get up that hill. So that was like some of the idea, the first law of thermodynamics, and the definition of work. And we want to like own those and be able to use them and be productive members of society. So that's video's long enough, and we'll see you in the next one. I'm not sure when I'll record it.